Okay, Badri, I will do my best to send you what you asked no later than tomorrow afternoon, okay?
Yes, yes.
So I already started to work on it, but it takes me a bit of time.
No, no issue. If required, otherwise I will prepare and I will send you. If you like.
I will do my best. I will do my best.
Okay, okay, no issue, no issue.
So, yeah. Now, yesterday we talked about adaptive beamforming. There is a part that at the end of the chapter that I would like to skip for the time being because I'm not sure we have time. So today I would prefer to start with the new topic, model-based beamforming. And then tomorrow, if you have time remaining, I can say something about the last beamformer that is described in the chapter on adaptive beamforming. So it depends on how much time remains tomorrow. So you have this chapter, right? Okay, we investigated classical beamforming, which is a non-parametric, non-adaptive method. So non-parametric in the sense that it does not rely on any model assumption for your data. Non-adaptive is because basically the impulse response of the beamformer does not require a priori knowledge of the correlation matrix of the data. So to be implemented, it does not need to estimate the covariance matrix. It does not require calculation of the sample covariance matrix. So the impulse response of the classical beamformer does not depend on the observed data. So in this sense, it is not adaptive. So the classical beamformer is non-parametric, non-adaptive. Then we introduce the concept of adaptive beamforming. Why? Because if you want to cancel or reduce the effect of interference in the best possible way, by solving an optimization problem, we found that the optimal beamformer, that we call clairvoyant beamformer, requires the knowledge of the correlation structure of the data. And because this information is not a priori known, we estimate from the data. And then we use the estimate to implement the beamformer. That's why the impulsive response of the beamformer becomes dependent on the data and so adaptive. The complexity increases, obviously, but on the other side, we design the beamformer in the best possible way, in the sense that we reduce at our best the effect of interference coming from different angle from the steered direction. The method that we have seen are so adaptive. So the sample matrix inversion beamformer, the K-home beamformer, minimum variance, distortion, less response beamformer, the diagonally loaded version of this adaptive beamformer. They are adaptive, but not parametric, since none of them rely on the assumption of a specific model for the data. Now, we know that model-based or parametric, I mean, the terms are synonymous. Model-based methods, in some applications, show to be very useful because they allow to exploit at the best knowledge about the structure of the data. And sometimes this information is available and so can be used to achieve better performance than non-parametric methods. In particular, you will see that by using some model-based method that I will introduce this morning, we can achieve a resolution that is better than the so-called Rayleigh limit. So the resolution of the classical beamformer that, as you remember, is the reciprocal of the number of sensors. So by using model-based method, we can separate sources that are spaced in the domain of the spatial frequency by less than 1/m. And this is very important. Now, what is the parametric model that we can assume for this kind of problem? Well, actually, we didn't exploit the best, but we already derived a parametric model for the array output data covariance matrix, which is a second-order statistic. Remember, the covariance matrix does not provide a full characterization of the statistical behavior of a random vector, because for all the information is contained in the multidimensional probability density function. So the covariance matrix only provides partial characterization, except the case where the vector is Gaussian. Because if the vector is Gaussian distributed, if you know the mean vector and the covariance matrix, you know the multidimensional probability density function, so you know everything. But in general, the data can be non-Gaussian, and so the covariance matrix represents a partial information, partial characterization of the statistical behavior of your data. But sometimes, this is enough to derive good algorithms. And this is exactly the case for model-based beamforming. So when I say parametric model, I need basically what is reported here. We derive this relationship. This relationship actually has been derived under the assumption that the noise is white. If the noise is not white, instead of the identity matrix, here you have another matrix. But what is important is that the covariance matrix of the signal of interest has a particular structure that depends on the geometry of the array, and we derive the dependency of Ry on vector theta of the unknown directional arrival. And so we derive the dependency, the law between the covariance matrix and the unknown parameters, which are the k directional arrival. So in other words, the vector theta. Then also the noise power can be unknown, and also the covariance matrix, the spatial covariance matrix of the signal can be unknown. So the number of unknown depends, but for sure, the directional arrivals are unknown parameters that we want to estimate. So this is a parametric model. Now the problem is, how can we exploit this result? Remember, I mean, this summarizes what you have already seen. So this is the array equation for k sources. This is the definition of steering matrix, the definition of the OA vector. Then you have the relationship between the directional arrivals and the spatial frequencies. S bold is the signal vector. RS is the k by k spatial correlation matrix of the sources. And this is the expression of the correlation matrix of the data in the case where the noise is partially wide. Okay. One important remark, because it plays a role, is the following. The signal covariance matrix, so ARS A Hermitian, has full rank K if the K sources are not fully correlated. If there are no couple of sources that are fully correlated. So in other words, the rank of the signal covariance matrix is equal to the rank of the matrix RS, which is equal to the number of targets or the number of sources. Obviously, this is true if M is greater than K. There is a case where this result is not true. The case where two or more than two signals are fully correlated. And this may happen, for example, in the presence of multipath, because the signal is generated by the same source. It arrives at the receiver following different paths slightly may decorrelate the signal, but I mean, they are correlated, and sometimes they are highly correlated. And so what happened is that the matrix RS can be either singular, so not full rank, or ill-conditioned, which is also a problem. Now, when the matrix RS is not full rank, we say that there are signals that are coherent. So the word coherent is synonymous of fully correlated signal. So the problem that we want to solve is to estimate the directional arrival. Now, if you are familiar with the power spectral estimate, and in particular, if you are familiar of the problem of how to estimate the frequency of a multi-component cosinusoidal signal that generates a discrete power spectral density, so a power spectral density with lines, you know that to estimate the frequencies of a multi-component signal, there are many methods. Nonlinear least square, relax, variant of relax are also very well known, like clean, sage. Then you can use the Uli-Walker method. You can use music, you can use Esprit. Now, because formally the structure of the data, in our case, is very similar to the structure of the data for a multi-component periodical signal, well, all these methods can be used to estimate the direction arrival. So I will show some of them, but actually all the methods that have been applied to estimate the frequency of a discrete power spectral density can be used to solve our problem. So to estimate the direction arrival of our signals. Let's start talking about those with the best performance. Unfortunately, best performance, but also highest computational complexity. So let me introduce the nonlinear least square method and the maximum likelihood method. Now, let's assume first, so we have to make some assumption. Let's assume that we don't know anything about the signal generated by the source. So we don't know anything, so we can model the signal samples, so the values of the M signal as M of N can be modeled either as a deterministic, completely unknown parameters, or the signal generated by the sources can be modeled as random processes with some distribution, for example, Gaussian. Then let's assume that the additive noise is white and Gaussian. Okay. Now, if we assume that the signal samples are deterministic unknown parameter, actually we have a problem. Why? Because when you increase the number of collected snapshots, you are increasing also the number of unknown parameters. So it's obvious that we have a consistency problem because the number of unknown increases with the number of collected vectors. And this is a problem. But I mean, so let's make this assumption. And so if the signal samples are unknown, we should jointly estimate the signal and the direction arrival, which is reasonable. We want to understand the direction arrival of the signal in the data, and we want to reconstruct the signals. So we want to be able to say at the end, from that direction, there is a signal of this kind. From this other direction, there is another signal of this other different kind, and so on. So we want to understand what is in the environment. We can address the problem by using the well-known nonlinear least square method. And the nonlinear least square method says that basically we calculate the difference between the data and the data model, the parametric data model, and we search for the values of the unknown parameters that minimizes the distance between the two. The distance is what? Is the energy of the difference. So we calculate the difference, and then we calculate the energy. The energy is the Euclidean norm square. Then, since we collect n snapshot, we average with respect to the n snapshot. So we sum with respect to n, and we divide by the number of snapshots. Now, you can observe that the functional that we want to minimize depends linearly on the signal S. There is a linear dependency. But unfortunately, the dependency with respect to theta is nonlinear. because A of theta is a nonlinear function. So this problem can be solved in 2 steps. The first step is we estimate S. And the estimate of S, I mean, it's a very well-known problem. It's a linear least square problem. So the solution of this problem is the pseudo-inverse, the more per rows pseudo-inverse of A, which is represented by this symbol and can be expressed in this way, that multiplies the data. So once we have an estimate of S, which obviously depends on theta, because A depends on theta. So we plug in our functional the estimate of S. So we put here the estimate of S, and what we obtain is sometimes called compressed functional. So basically, we eliminate the dependency on the linear parameters, which are the vector S. So if you write explicitly S at, it is the pseudo-inverse of A, this matrix here, times Y. Now that you have this term, you can put Y of n in evidence, and you can write this matrix here in square brackets that multiplies Y. Now, what is this matrix in square brackets? It's a projection matrix. And in particular, A pseudo-inverse is the projection matrix onto the subspace generated by the column of A. So it is what sometimes is called signal subspace. The identity matrix minus the projection matrix on the signal subspace is another projection matrix, but it projects the data on a subspace orthogonal to the subspace generated by A. So if PA is the projection matrix onto the subspace generated by A, which is k-dimensional, I minus PA is a projection matrix onto the orthogonal subspace. So we denote by using this symbol. So in other words, the function that we should minimize is what? Is the energy of the component of Y onto the subspace orthogonal to the subspace generated by the column of A. So you should change theta. If you change theta, you change A, so you change the subspace, and you should find the values of theta that minimizes the energy of Y on this orthogonal subspace. I mean, I don't know if you are familiar with the concept of projection matrix, but if you multiply A by the pseudo-inverse of A, which is this one, what you get is a projection matrix. So when you multiply the vector Y, so your data vectors, by matrix PA, what you get is the orthogonal projection of Y onto the subspace generated by the column of A. So you find the component of Y that lies in this subspace. Now, all the projection matrices have these 2 important properties. All of them are idempotent. So PA is equal to PA squared is equal to PA to the 3rd power, to the 4th power, and so on. And any projection matrix is Hermitian. So if it is real, it is symmetric. If PA is the projection matrix on the subspace generated by the column of A, this subspace is typically called range of A. I minus PA is the projection matrix onto the orthogonal subspace. And so, in other words, PA orthogonal project a vector onto the what is called the null of A. The null of A is the subspace orthogonal to A. Now, we need to minimize this function with respect to theta. We can express this functional in a different way. So if you express the Euclidean norm square if you express the Euclidean norm square as of a vector, this is a vector. So you express the Euclidean norm square as a vector Hermitian times the vector. Then you calculate the Hermitian. So this is the Hermitian of PA orthogonal Y. So you have the Hermitian of Y that multiplies the Hermitian of this projection matrix. But because it is a projection matrix, it is Hermitian. So what you get is PA orthogonal that multiplies PA orthogonal. So you get this. But because it's a projection matrix, it is idempotent. So this matrix square is equal to this matrix. Then you can express this quantity, its well-known property of the trace. This summation is equal to the trace of PA orthogonal Y Hermitian. So the trace of what you get by bringing Y Hermitian at the end. So the trace is linear. So you can PA orthogonal does not depend on n, so you can bring outside the summation. So what you get is the trace of PA orthogonal times 1 over n, this summation. And this is nothing but the sample covariance matrix. So at the end, you can express the functional that should be minimized with respect to theta in terms of the well-known sample covariance matrix. And what depends on theta is PA orthogonal. Because PA orthogonal depends on theta through A, because A is a function of theta. So at the end, we should find theta either by minimizing this trace or maximizing the same quantity in the orthogonal subspace, so in the subspace of A. So you can minimize this with PA orthogonal or maximize this with PA. The solution is the same. So in other words, the estimate of the directional arrival is obtained from those values that minimize or let's say that maximize the energy of the received data of the component of the received data onto the subspace generated by the column of A. Now, it's clear that in order to find an estimate of the K directional arrival, we have to solve a K-dimensional optimization problem. And this problem is nonlinear. So, I mean, the estimate that we obtain by applying the non-linearly squared method a very high computational complexity. This is the problem, because they need multidimensional, in particular k-dimensional search. So, and this is the main problem of the nonlinear least square method, because in terms of estimation accuracy, the estimation accuracy is very good, it's very high, and asymptotically it coincides with the estimation accuracy of the maximum likelihood method, which is the best possible that we can apply. So the problem is computational complexity. This is an example where we have two sources, 10 sensor, 128 snapshot, signal to noise ratio 0 dB. So we have two sources, so we have to solve a two-dimensional optimization problem. We have to find the position of the peak in a two-dimensional space. Now, here there are two peaks. Why? Because obviously, if you have two sources, you can call θ1 the direction arrival of one source and θ2 the other, or the reverse. So there are two different ways to assign a label, a name to a source. So, but for example, if we decide that θ1 is the smallest between the two, so θ1 should be smaller than θ2, you don't, so θ2 is the smallest, sorry, θ1 is the smallest, θ2 is the largest. Well, in this case, the search should not be done over the entire square, but if θ2, sorry, if θ1 is smaller, basically you limit your search on the upper triangle. If you make the reverse assumption, θ1 greater than θ2, you can limit your search on the lower triangle. So in any case, whatever you decide, you can limit the search only on one triangle, and in one triangle you have a single global maximum, and so you have to find the abscissa and ordinata of the position of the global maximum. And the abscissa and ordinata will provide you with the estimate of the two-directional arrival. Clearly, the problem is that the functional is non-linear. And in addition to the global maximum that is here, you have many local minima and local maxima. So if you use an iterative algorithm like the gradient, or I mean, there are many, the algorithm, and if you start not close enough to the global maximum, the algorithm converge to a local maximum. And so it can provide completely wrong estimates. So the initialization is very important. These are two different ways to plot the functional. If I remember, this is linear, this is in dB. I mean, more or less is the same. So in summary, the functional that we have to minimize or maximize is the same. As many local maxima. So many local optima. So this is a problem. This is a problem because if you want the algorithm to converge to the optimal solution, the initialization should be made in a very careful way. And this is not simple. Obviously, the solution can be obtained only by numerical methods. It cannot be found in closed form. And the computational complexity increases exponentially with the number of targets, with the number of sources. So if k is the number of sources, we have to perform a k-dimensional search. And if k is greater than 3, I mean, the complexity becomes too high, especially if you need an estimate in real time. So if you don't need an estimate in real time, okay, you can delay the outcome. But if you need an estimate in real time, so with a short delay, forget this method because the computational complexity is too large. Actually, we can prove that if the directional arrival are well separated, to solve the nonlinearly squared problem is basically equivalent to apply the classical beamformer. Or in other words, the classical beamformer, so finding the k largest peak in the output of the classical beamformer provides an approximate solution to the nonlinearly squared problem all the times that all the directional arrival are well separated. Why? Because if the two angles are well separated, so it means basically the difference between the two angles is such that this quantity, remember, these are the spatial frequencies, so the difference between the spatial frequency is greater than the Rayleigh resolution, 1 over m. In that case, we can approximate this inner product, A Hermitian A, with 0. So these two vectors are approximately orthogonal. Now, if these two vectors are approximately orthogonal, A Hermitian A is basically proportional to the identity matrix. This can be proved very easily. So the projection matrix of A approximately can be expressed in this way. And if you plug the projection matrix here, we can prove that this trace is equal to this summation. Here there is the proof, but I mean I'll skip to discuss the proof. It's something related to properties of matrices. So if all the sources are well separated, this functional can be approximated by this functional. And if you solve the problem on the right, basically the solution of the problem on the right is the k largest peaks in the estimated power spectral density, so in the power spectral density estimated by the classical beamformer. Because if you remember, the expression of the estimated power spectral density by using the classical beamformer is this one. So we want to maximize, so we sample in k places the power spectral density and we sum. And what we want to find are where to sample, where to calculate the power spectral density in such a way that the sum of the value is the largest possible. And obviously the answer is that sample at the k largest peak. So this maximization, which is approximately equal to this maximization is obtained by selecting the k largest peaks in the estimated power spectral density obtained by the classical beamformer. And so, in other words, if the sources are well separated, the performance of the classical beamformer for DOI estimate tends to be equal to those of the nonlinearly squared method. It is a very efficient method, very high performance. So that's why the classical beamformer is so widely used, because it's a very robust method and its performance are close to optimal if the sources are well separated. So when we should not use the classical beamforming, if we think that there can be a problem related to the resolution. If we think that in the data there could be sources that are closer than 1 over n. In that case, so if you want to achieve better resolution, don't use classical beamforming. So you should use either capon. We have seen yesterday that the peaks of capon are much narrower, so it has much better resolution than the classical beamforming, or use a model-based method, one of the method that we will see today. I think it's the good time to have a break.